Okay, so we've done a bunch of gas laws. We've done Boyle's law, Charles's law, Gay-Lussac's law, ideal gas law, a whole bunch of gas laws. So we're going to step away from that for a little bit, and we're going to talk about stoichiometry with gases. And so when you're doing stoichiometry, typically what it is it's grams of one thing, and then you're going to multiply by something to change it into moles of that thing by using the molar mass off the periodic table. Then you change from moles of one thing into moles of something else. And these are using the balanced equations. Okay? And this is what makes it stoichiometry, when you change from one chemical into another chemical. And at the very end, you change from 1 mole of that chemical and 2 grams of that chemical using molar mass again. So you might remember doing this. Well, when it comes to gases, we're going to do essentially the same thing, except we're going to use STP to kind of help us. So just to refresh your memory, STP is standard temperature and pressure. Is the value of 0 degrees Celsius in 1 atmosphere. And here's the big thing. 1 mole of any gas has a volume of 22.4 liters. And it is a conversion. 22.4 liters is 1 mole, as long as it's at STP, or 1 mole is 22.4 liters, again, as long as it's at STP. So you can use this like a conversion, and I did show you some problems in a previous PowerPoint on how to do this. Okay, so I'm not going to do those again, but we're going to talk about how to go straight into stoichiometry. So it's just like stoichiometry that you've done before, except you're going to deal with volumes of gases in addition to the mass, that was what we're used to, the grams. Okay, make sure your equation is balanced. I know it's been a while since you've done that. I'll probably come back to you. If the system is at STP, you can use those conversions. 1 mole, 22.4 liters, or 22.4 liters is to 1 mole, to convert liters into moles or moles into liters. That's got to be at STP. Use the balanced equation and convert moles, and you should be good. So let's take a look. So balance this following equations. Take a minute, see if you remember how to do this. Okay, you probably start by putting a 4 here and a 5 here, but what that'll do is it'll give you 8 plus 5 will give you 13 oxygen. So if you remember, when we're dealing with odd numbers of atoms, one of the hints I told you guys was to double everything. So double this, and double that. 8 times 2 is 16, plus 10 is 26, put a 13 there. So now you don't have an odd number of atoms. So 25.3 liters of oxygen reacts, and here's the important part, at STP. What volume of water is made at STP? So we're going to start with the number and the unit. I'm going to erase that. Let's try that again. I'm going to start with the number, 25.3 liters, and I'm going to call it oxygen. And I'm going to put liters in the bottom, and I'm going to change it into moles, because when you use stoichiometry, that's one of the first things you do, is if you're not given moles, you change it into moles. Since it has STP, you can use 22.4, and liters cancels out. Then oxygen into water, and that's where I use my balanced equation, 10 waters, 13 oxygens. Oxygen cancels out. Last step, they want volume. That means I need to have liters at the end. 1 mole, 22.4 liters, as long as it's at STP. When I multiply this all through, you get 19.5 liters. So when you're doing STP, it's kind of like doing grams to moles, except on the bottom you don't have grams, you have liters. So now when it says grams, what you're going to do is 72.5 grams. Grams on the bottom, 1 mole of C4H10. Add that up, it's 58 off the periodic table. It took 2 of the C4H10s to make 8 carbon dioxides. That's from the balanced equation on the previous slide. And then 1 mole of any gas, they're looking for volume, liters on top, 22.4. And now you've got a problem that is a little bit more complicated, but not too bad. You get 112 liters. Now you may have noticed in the previous slide, we started with the liters. We ended up dividing by 22.4 liters, 1 mole. And later on, we ended up multiplying by 1 mole, 22.4 liters, which means essentially those steps don't count. And that does occasionally happen. Anytime you're going from volume to volume at STP, they will cancel out. All right, so now here's a different balanced equation, except it's not balanced properly. It should be a 13 here. Okay, 96.3 liters of water is made at STP, so pay attention to your units. Liters in the bottom, 1 mole is 22.4 liters, cancels out. It took 10 waters from 13 oxygens, so waters cancel out, but they want mass. So 1 mole is 32 grams for oxygen. So you have to just pay attention to units. They're not really that different from anything we've been doing all along, but if you don't pay attention to units, you could very quickly find yourself kind of in a mess. Okay? Pay attention to the units, what you start with and what they want at the end. Well, what happens if it's not at STP? Well, if it's volume to volume, like I said, it'll work. So you can just use the mole ratio to convert volume to volume, even if it's at 1,000 degrees Celsius and 400 atmospheres. As long as it's the same temperature and pressure, you can just use the mole ratio because the end steps cancel out. However, if it involves grams, you have to use PV equals nRT to convert to moles. So let me do this problem. Put a 2 and a 2. Okay. 25.9 liters of oxygen reacts at 100 degrees C and 96 kPa. What volume of water? So it's volume to volume. Here's the cool thing. 25.9 liters of oxygen. Since it's volume to volume, even though the temperatures are really different from what you would expect, and the pressure too, all you need to do is do this mole ratio. 1 oxygen, 2 waters. And you're done. As long as it's volume to volume, it's okay. They will all cancel out. 51.8 liters and you're done. Only volume to volume, you can use just the mole ratio from the balanced equation. But if it involves grams, guess what? Not going to work that way. So you have 25.9 grams of oxygen, reacts at temperature and pressure, but grams, it's not affected by temperature and pressure. 1 mole of oxygen, 32 grams. It takes 1 oxygen to make 2 waters, and then the water is at STP. And if it's at STP, all you need to do is plug it in and solve. You get 36.3 liters. Okay. A couple of reminders for you about stoichiometry. Since it is stoichiometry, all the same things that we've done with stoichiometry in the past count. That means percent yield is a possibility. Okay, just refresh your memory on that equation. It also means that we can do limiting reactants. Okay, whichever reactant makes the least amount of the same product will limit how much you can make. Remember, you're picking the smaller number with this. You're going to see some of those in the homework packet. Okay, just be aware that anything we did with stoichiometry earlier this year is fair game. Okay, this is a quick summary of the gas laws. I think it might be in the notes. We'll talk about this one next. That's called Dalton's Law. It's the last one.